for invitation. So I will report my joint work with Weber and Finkelberg. So I started this hyperkähler quotient construction, so which we already had in the previous talk. So let K to be a compact Lie group. So I only consider the hyperkähler quotient of the vector space. So I take M. This is quaternic vector space, quaternic representation of K. Then by teaching Carl-Lindström logic, so you consider hyperkähler quotient, Dirac quotient. So which is just, so I denote this by M triple slash by K. So this is the singular hyperkähler reduction. So you consider moment map, and you take the level set and the quotient by K. Sometimes I consider this to be affine adjoint variety. So in that case, I regard this to be level set of complex part. So maybe I denote. Mu is hyperkähler moment map. So this decomposes into real part and the complex part. So you take level set of the complex part of the moment map and divide by complexification of C. So this is a description of hyperkähler quotient at affine adjoint variety. So, but if you read carefully the paper, so you know that this hyperkähler quotient construction is coming from physics. So this underlying physics here is three-dimensional quantum fields, three-dimensional n equal for supersymmetric quantum field theory. So more concretely, so once you have a group and representation is given, then you consider the corresponding gauge theory. So the gauge theory is about connections of a bundle, K bundle, and also section Higgs field, which is just a section of bundle, K bundle twisted by this M. So anyway, this hyperkähler quotient construction has origin in physics, and this hyperkähler quotient construction is called Higgs branch of the three-dimensional n equals 4 supersymmetric gauge theory. The physicists also consider the so-called Coulomb branch. Of supersymmetric gauge theory. So this is another hyperkähler manifold. With SU2 action, rotating hyperkähler structures, and if you fix complex structure, then you have U1 action preserving this complex structure, and a non-compact. And classically, it is it looks like, so I denote this by MC. So classically MC looks like R3 cross S1 times rank of K divided by Weyl group. So it's very similar to the monopole moduli space, whereas also monopole moduli space where separated monopole moduli space, it looks like this, just which we just ran in the previous talk. So in fact, this monopole moduli space will be a particular example of some special choice of K and M, which I will explain later. But
does this SU2 action actually Is it related to the Swan bundle over a quaternionic manifold or not? I mean, often that's the typical place where you see an SU2 action that rotates.
You want to see some quadratic Taylor manifold under MMC? I don't know. So it could be interesting, but this is so this is as in the case of monopole modular space. This is only classical picture. So you have quantum collection. So this means, I mean, for mathematicians, this means there is no mathematical rigorous definition for MC. But nevertheless, I mean, physicists know have many examples of MC, starting from explicit B, G, K, and M. They know many examples of MC. So the problem, which I just want to discuss today, give a rigorous definition. So that it satisfies all those physical expectations. And also, so this is just a remark, but I want to mention that. So this Higgs branch, this is M divided by K, and Coulomb branch. They are very different. For example, dimensions are very different. So dimension of quotient is dimension of M minus dimension of K in quaternion sense, and this is just the dimension is rank of K. So the dimension, for example, the dimension is, so they are very, very different, but there are some mysterious relation between them. So sometimes called three-dimensional mirror symmetry, or symplectic duality. So even if you are only interested in this kind of hyperkähler quotient, you should also understand this MC.
How is the representation encoded into the Coulomb?
So far not. I mean, so just in this, it is independent of the presentation, but I'll explain. So today, I give partial answer. So first of all, I need to assume M is direct sum of complex representation of, this is a complex representation of K. And M is of the form n plus n star. In fact, there are a lot of, this is not so big assumption. There are many examples of this form. And I define MC as an affine algebraic variety as a spectrum of some graded commutative ring. So I give an explicit construct definition of graded commutative ring, and so MC is can be recovered as its spectrum. And the grading gives us a C action on MC. So this is the C action which is the restriction S action preserving the one particular complex structure. So this graded commutative, in other words, this graded commutative ring is the space of functions on MC. So I define this ring.
So the form of the representation already chooses a particular complex structure, and then this is a description.
MC, yeah, in the definition I use the representation. So the main question is, the main problem is that describe hyperkinetic. So in general, so MC has a singularity. So more accurately, so this definition should be considered as a partial compactification of the Coulomb branch. But anyway, so on this smooth part, we can expect that there is a hyperkinetic. So before going, giving the definition of this ring, so I give some properties of this Coulomb branch in our definition. So this is, first of all, this is affine analog. Yeah, in fact, yeah. So we don't know that this is irreducible and normal or such kind of things. So this, we have a finitely generated graded commutative ring. So MC is just affine scheme in a strict sense. So anyway, this is the first property, and also, we can see this classical description. MC is birational to T star T check divided by Weyl group. So T check is a dual torus of complexification of maximal torus of G. So you just replace R3 cross S1 by C cross C star. So in that sense, I mean, I just our definition passed the first test for this, and also, so this is somehow interesting byproduct from the construction. But this MC is equipped with the integrable system. So you have a natural fibration over the vector space. So in fact, the vector space is just the algebra of T. So T is complex system and Y. And and this is just vector space. It's known to be vector space, and each component of this function are Poisson commuting. So I should also say that we don't know that this is to be hyperkinetic, but we know that this has a Poisson bracket. So this graded commutative ring has Poisson bracket. So this Poisson bracket is expected to be Poisson bracket to be given by the holomorphic symplectic cone. So this is so in some sense, I mean, this reminds me the Hitchin system. So modular space of Higgs bundles to this characteristic polynomial of Higgs field is a Hitchin system. So it's something similar. And so this is a half dimension, maybe. This is a half dimension, right? So this is twice rank, dimension is twice rank, so this is half dimension. So in that sense, this is and you can also show that the fibers of phi is a dual to dynamic fiber. And also,
So the Poisson bracket is supposed to correspond to the holomorphic 2 form, right? Not
holomorph, yeah.
but this math is phi to the real form?
This is the holomorphic. So from now, I'm basically only use complexified groups, and so I will never use compactly group from now. Probably, I don't know. Yeah, anyway. And also, I can compute the. So this is graded ring. So I can consider the character, its character. So this is some combinatorial expression, and this corresponds to the monopole formula, which was found by Coulomb and Zaffaroni under some assumption, under some mild assumption. So this is some explicit combinatorial expression. So I mean, I will talk about this, so I will not go into, I will not explain. But anyway, so this is one of the tests to check this our definition is correct. And we can identify in some special cases. So I first consider the case m equals 0. So 0 is also allowed. 0 is triviality. Then MC, our MC, we can show that this MC is moduli space of solutions of Nernst equation. On interval, and for to write down the Nernst equation is ordinary differential equation of connection and Higgs fields. And so to talk about the connection, so we first need to take a bundle, a principal bundle. So I take this principal bundle with K check, which is Lagrange dual of K. And I choose boundary condition. Boundary condition is the one which you see in the description of monopole modular spaces. So at plus minus 1 pole of you have pole of first order, and the residue this residue equals. Residue is homomorphism from SU2 to K check, and this corresponds to regular nilpotent. So you extend to this homomorphism to compressification, then SL2 to G check, and this image of the element E in SL2 goes to principal nilpotent. So this is there's this. I use the relation between SL2 triple and the nilpotent orbit. So in particular, from this, you already see that. So this is, as I said, when K is a unitary group. So this is the description of monopole modular space by Nernst. So from this, k equal un, and m equals 0. At least as a complete symplectic manner.
What's the SU2 action in general?
Pardon?
SU2 action.
SU2, I don't know how to construct SU2 action. First of all, I only know how to construct the U1 action. So because this is a complex algebraic description, so I don't know how to construct this. But anyway, in the left-hand side, of course, it's known.
I'm sorry, but once you gave this identification with the norm equations, it's just SO3 rotating the three norm matrices.
Yeah, but I want to have, so Thomas asked me the SU2 action in terms of MC in my definition, in our definition, which I don't explain yet.
As a spectrum, you mean now?
Yeah, so I so far I just define in this way, and I can see, so this is a graded ring, so you have ceased action.
So this description focuses on a particular complex structure, and it's very difficult to change. I mean,
Well, but all of the complex structure is equivalent, so in that sense, I mean,
Yeah, but you chose a complex structure, so you only see the S1 which preserves this complex structure.
yeah. So I mean, of course, I mean the natural approach to this second problem is to construct a twistor space, and if I can construct a twistor space, then probably I can see the SU2 action.
Once you know SU2 action, you know the hyperkähler structure pretty much.
Yeah. So next case is the case K is torus. Then MC is dual dual toric hyperkähler manifold of MH. So what is dual? So I have K in this hyperkähler toric hyperkähler manifold is a quotient of vector space by torus. So I have a homomonism of K to U1D. So U1D acts on HD in the usual way, and the K I can consider K to be subgroup of it. And then I have quotient K prime. So I assume that this K prime also to be torus. Then the dual hyperkähler manifold, dual toric hyperkähler manifold is a quotient of HD. This. By dual torus of K prime. So if you go into dual, then this exact sequence is swapped. So you have K prime dual. The middle one is self dual. So you have this short exact sequence. And in particular, K prime dual acts on HD. So this is the definition of dual. Okay. So next, I consider the case when I replace SU2 by other groups. By the way, so all those examples are so far already known in physicists. So all these are somehow ticks, so that our definition is correct. Maybe for yeah. Maybe for this example, so people only know the case unitary group and classical groups, but it's natural generalization. So anyway, so I take quiver, the so-called quiver gauge theory. Of type AD. So I take a Dinkin diagram of type AD, for example, like this. So this is D4. And I choose that orientation for each edges, so for example, like this. And I put numbers, positive numbers to each node, N1, N2, N3, and N4. Then I take K to be product of UN1, UN4, and N to be space of homomorphism from C of Ni to Cm and J if you have arrows in this direction. And M is N plus N. So if you consider the Higgs branch of this, then you can show that this is always zero. So the solution of moment work equation is only have zero. So in that sense, I mean, Higgs branch is not interesting, but still Coulomb branch is something non-trivial, and MC is in fact this monopole modular space for general groups.
So the Higgs branch is the zero quotient, so you quotient it.
Quotient by zero, yeah.
So there is maybe some stack structure on this.
Yeah, yes. But so anyway, so MH, in my definition, MH is mu inverse 0 divided by K. So if you use this definition, it's always 0. MC is monopole modular space. The group is corresponding. So this group is given by Dinkin diagram. So if this is, for example, in this case, this is D4. D4 is SO8 or something, yeah. And those numbers are monopole charges. and so for SU2, you have only one monopole charge, but for arbitrary groups, so you have monopole charges for each vertex. And so for A1, for Dinkin diagram of type A1, you have only one circle and no arrows at all. So you recover this, the previous one.
So these are monopoles with maximal symmetry break?
Maximal symmetric break. So far, I don't know how to construct the other symmetry break. And there are some variants of which I'd like to mention. So you can replace any this diagram. So there's no reason for us to restrict to the AD Dinkin diagram. So you can consider more general arbitrary graph, and you can define group and representation in the same way. In general, I don't know the answer, but I know the answer for affine case. Affine linking. Then you get modular space of Coulomb. Coulomb is just instanton zone R3 cross S1.
You got the R and the L interchanged.
Huh?
Japanese mistake. You got the R and the L interchanged.
Oh, really? Okay.
Same in Japanese, right?
Oh, yeah, it's difficult to pronounce for me. Yeah. And for, I mean, yeah. And also you can consider also framed representation of quivers. So this is so the Higgs branch is the so-called quiver varieties. So in this Dinkin diagram, you also add the squared boxes, and you put also integers, positive integers, non-negative integers. Then k is the same, and m, or n is at Holmes from n I to double I. So this is. Then you get the modular space with singular monopoles. So the Higgs branch is quiver variety, Coulomb branch is modular space, singular monopoles. I mean, again, this is for type AD. I don't know what happens in genus. So let me see. Modular space of singular. So singular monopoles is defined, so this is defined over R3, but it has singularity at the origin. And one way to understand this singular monopole is that the S1 equivalent instanton zone tabular. So if I consider the affine case, the similar framed representation of affine quiver, then so conjecturally affine, framed affine. So this is conjecturally instanton zone. The actual instant on tab not, or possibly tab not divided by this type A or type D. Where type D, I don't know. Yeah, type A group.
Now the Higgs branch is also non-trivial.
Higgs branch is quiver varieties. I don't know quiver varieties is trivial or not. Someone say finite dimensional quotient is something simple, so. Okay, what else should I say? Another thing. So before going to the research, so this one interesting corollary of the construction is this coordinate ring, this non-commutative, I just erased, has a non-commutative deformation. So which I denote by H bar. So H bar corresponds to Planck constant. So So if you make h bar to be 0, and h bar is defining, this is defining polynomial, not the formal one, so this is polynomial in h. So this is, if I take h bar to be 0, I recover this. And this, in fact, this non-commutative definition I already implicitly used. So this simplex Poisson, I mentioned this Poisson bracket. This CMC has a Poisson bracket. So this is defined by using this non-commutative deformation. So I consider AB minus BA. So since this is non-commutative, AB BA is not necessarily 0. But if I specify h bar to be 0, then this becomes 0. So I divide this by h bar, and then make h bar equal 0. So this is the usual definition of Poisson bracket once you have a non-commutative deformation. So in that sense, somehow this non-commutative deformation is quite natural, and I don't know, there are some people who studied the quantization of this kind of monopolar modular space, and so it is expected that this h bar is something which have already studied. So anyway, so this is the description of properties. So now I start with the definition of this. Any question so far?
Can I ask where does that non-commutative structure come from?
Yeah, I will explain. So it's somehow it is naturally equipped with the definition of this commutative ring. So this construction is divided by 2 steps. So from now I consider just complexification, and N is a representation, usually complex representation of G. So given G and N, I construct some space, which I denote by R. So this is infinite dimensional. Variety. And you have an action of infinite dimensional group, those polynomials with values on G. So you have this action. So this is infinite dimension. And this is very close to the so-called affine Grassmannian. So the definition of this space is the first step. This R itself can be considered as a kind of modular space. Define convolution product. Usually a circle on this homology, equivalent homology group of this space. So this is the definition. So this. So this is not the cohomology. This is a homology. So the cup product is of course if you consider cohomology, the cup product is a natural product, but this convolution product is very different from the cup product. And in fact, if you look at the definition of the convolution product, then somehow it's not so obvious to that this product is commutative. So showing that this to be commutative is another step. So anyway, so if you change the construction slightly, then you get non-commutative deformation. So basically, I consider C star action on the formal disk. So this is spectrum. So all those spaces, group and space are defined over formal disk. So there's if you have a C star action on the formal disk, then it naturally induces a C star action on this space. So you can consider equivalent homology of GZ cross C star of R. So maybe you must pick skip product. So then this is a non-commutative deformation. So equivalent parameter appears from equivalent cohomology of C star of a point. So this is a polynomial ring in one variable. So this H bar appearing in a non-commutative deformation is the equivalent parameter.
Formally, this is sort of like every fiber away from 0 would be the same, but
Yeah.
then it jumps to something
Yeah,
else.
yeah. In fact, it is a flat family. Then the classical description, which I mentioned, is coming from the localization theorem in equivalent homology. So I record MC is birational to T star of T check by Weyl group. So this description is a consequence of localization. For equivalent homology. Equivalent homology.
This is only a binary-morphic
Yeah, I explain soon. Yeah, so you consider H star of G, but this is just, you just replace G by T, and you take, so this is, you have no Weyl group action, and if you take the Weyl group invariant part, this is H star. And this is, so if you tensor this fractional field, so this is a module over equivalent cohomology of point. So in fact, so you don't need, for equivalent cohomology of point, there's no difference between the formal power series in T and just the constant T. So you tensor this fractional. Then the equivalent localization theorem for equivalent homology group says that this is isomorphic to, by inclusion, this is isomorphic to equivalent homology of fixed point of the torus action. Right? Then you just study what is RT. So this is, maybe I will explain what it is in later, but this is something easy space. And you can directly compute this. And you get this. So in general, so people interested in the asymptotic behavior of the metric, so far we can talk about the complex structure, but somehow this is a hint for general description. You can consider, so the more take a smaller abelian groups, and if you consider the fixed point of the smaller group, then somehow you can see the asymptotic structure.
How does the representation fit in?
Yes, it is hidden in definition of R, which I don't explain yet. R depends on G and N.
So what is R for monopoles? What is R for monopoles?
For generally, it's a general construction. It's nothing special for monopoles. Yeah. Anyway, so it must be based on this kind of representation.
Can you relate to the Higgs branch of the other theory?
Huh? What?
Can you take this two-step procedure and relate to the Higgs branch?
No, I don't see anything. Higgs branch is something much more simpler and just hyperkähler quotient. So Coulomb branch is more sophisticated. So you don't have any simpler construction. What else? And also integrable system. Integrable system is also integrable system. This is coming from H star of 0 point. So you have this H star of G equivalent homology where any space is a modulo over equivalent homology point. So this is just, and this is polynomial. So this is integrable system. And you can show that this is indeed Poisson commuting. Okay, then I need to explain the definition of R. So I first consider the case when the representation is equal to 0. So for SU2, this is enough. For SU2 monopole, this is enough. Then R is just affine Grassmann. By the way, so I should mention that this affine Grassmann is a very, very basic object in geometric representation theory. So this is a kind of a flag manifold for infinite dimensional Katsumudi group, affine Katsumudi group. Partial flag. So anyway, this is defined as a quotient of Hoffman-Roland power series with value in G divided by G of G. And you have remaining action Gj from left multiplication. So this is it. So then you consider equivalent homology. Then I need to define the convolution product. So convolution product is the convolution, the usual. I hope you know that the convolution product for functions, but so the convolution product makes sense for homology group. So this, so not really product, but you consider slightly twisted product. So anyway, but you consider the affine Grassmann bundle over affine Grassmann, yeah? Instead of just naive product. Then you have P1. P1 is just projection to this quotient, and you also have quotient by this. So this is, strictly speaking, this is mapped to the quotient of Grassmannian by this. And also you have multiplication. So you multiply both elements and then you get. So then C1, C2 is defined by M star of C1 star of C1, C2 star. So you have homology class C1 and C2. Then you just put back by P1 and P2. So equivalent homology of this is just the homology of the quotient. So you can put back from here. And then you just go this one. And then somehow the role of first factor and the second factor are slightly different. So it's not so clear that this to be committed, but you can show that this is committed. And in fact, this case, the construction is older, and this case was considered by Bezukavnikov, Finkeberg, and Markovits. I don't remember which year, but.
So for the cat product, you're in infinite dimensions. How does
So you must be careful that this, so I should mention that this affine Grassmannian is infinite dimensional space, but you can approximate by finite dimensional spaces. And so the actual definition of the homology group is the limit of this, equivalent homology of this finite dimensional limit, and take the limit. And all these things.
When you take the limit, do you shift the gradients? Or do
Yeah,
you
for this you don't need to, but for R I need to shift the degree. So this is the definition, and if G is a torus, then it's something very, very simple. This affine Grassmannian is homotopic to just lattice, the so-called covariant lattice. This is the space of homology. C strategy. So this is called covariant lattice of G. So affine Grassmannian is just a bunch of points. Points parameterized by covariant lattice. So this is just lambda times for each lambda point in each lambda is just a point, but you still have non-trivial trivial actions of group. So you must take the product of H star of G of point. And this is just polynomials on the real level of G, and this lambda corresponds to function on the dual torus. So this is C of. So basically, the classical description, which I just erased, the fixed point here is basically affine Grassmannian for torus, and we just get this kind of description. So I finally explained the general case. General N. So affine Grassmannian, so this is one way to understand affine Grassmannian. Yeah, in fact, this is set theoretical description. The affine Grassmannian is a moduli space. Moduli space of pairs. P and phi. So P is a G bundle over P, over disk. And phi is a trivialization of P over functional disk. So so this is just the how to say given by the trivialization. So any G bundle over disk is can be trivialized, and this function is given by comparing the trivialization and the trivialization given by this phi. So anyway, so this is well-known description. Modular space, description of affine Grassmannian modular space. In fact, you can consider similar things for arbitrary Riemann surface, and you get the modular space of bundles. And the affine Grassmannian is closely related to the modular space of bundles on a curve, on the Riemann surface. Then from this, somehow you can consider the following natural space. So you consider the vector bundle over affine Grassmannian. So this is a modular space of triples P, phi, and S. P and phi are just as above, and S is a section of the associated bundle E cross G. And R is cross the subvariety mean. So this is the infinite rank vector bundle over affine Grassmannian. And I impose the condition that, so I send this section by this trivialization. So this is a rational section with value in n representation, but I impose this to be actually it extends across 0. So this is a priori here, but I assume that. So this is it. And on here you have an action of the G, and the definition of the compression product is slightly complicated than this, but you can play similar game. You can have a kind of product for R, and you have 3 projections, and you define compression product in the same way. So this is the definition of R and compression product. So thank you for attention. Nice.
Any questions for the speaker?
So you said a few things that indicated this has to do with geometric line lengths.
Well, affine Grassmannian is natural, natural appearance geometric Lagrange, and so Lagrange group appears everywhere. I mean, you start with. So I mentioned that the n equals 0 case, you get the solution of Nernst equation, but the Nernst equation must be considered on Lagrange dual of the original group which you consider. Yeah.
So how do you get it? Can you see Nernst equations now?
So I didn't say how I prove this. So this they proved that they computed this thing, and so they say that this is something to do with Toda system, and then I mean, so I just look at your paper, and this is the same as your description for Nernst equation for this interval with regular force at the end. So in that sense, I mean, for n equals 0 case, I really don't need to compute it. Just quote the previous letter.
So you're saying as a complex manifold,
Yeah, as a complex manifold, they compute it.
They compute it as a complex manifold.
Yeah.
And then you do what?
I read your paper, and I about NAM's equations, and you have a complex description of the solution of the NAM's equation by slices, right?
Okay.
So then I just match.
Okay. Very well.
Yeah.
In the quaternionic case, is connectivity also be related to the monopole? So if now the representation is quaternionic, I mean, I thought you're looking at complex representations now.
No, I assume so M. I started with quaternion representation, but from some point I need to assume M to be direct sum of N plus N star. So this is a quaternion representation, and N is a complex representation.
Okay, but like you always split it like this.
Yeah. If I don't have splitting, I don't have the candidate for R. So somehow so in more general case, I need to modify the definition, but so far I don't know how to do it.
The hypercalometric? Okay. Can you see the hypercalometric?
No, that I made as a problem prime. So you should construct a twistor space.
So to start with quaternionic affine Tasmanian.
Well, that's too much.
Do you see in the formalism distinction between cases where the monopole operators get negative values of delta?
That I didn't quite mention, but this you said the theory is good or ugly.
Yeah.
So otherwise the monopole formula doesn't make sense. But this condition means this weight, C star weight, is positive, and the only constant is weight 0, and but our construction is general, so I don't need for monopole modular space, for example, C star weight can be both positive and negative. So the monopole formula, if you write down the monopole formula, it doesn't make sense because you have infinite sum. So to make sense for the, I mean, if you cut out the formula in finite sum, then it always makes sense. But the sum is not well defined unless you assume this condition. So in particular, it means that the weight space could be possibly infinite dimensional. So in that sense, monopole formula doesn't make sense, but still space itself is defined.
There are no more questions, and let's thank you again.